Hi everyone, we're going to be going through the section 2 worksheet for CS188. Let's just get started with the first problem, which is called search and heuristics. The idea is, you can take a minute to pause the video and read through this description, but essentially I'll just describe what it says. It's referring to a maze-like search problem, and a depiction of that problem is over here. And the idea is, it's a problem very similar to other search problems that you've seen in this class, specifically, maze-type search problems where you have some goal, which is a square in this maze, and then you have some starting point, and you're trying to get from the starting point to the goal, and you have walls which you cannot walk through, right? That's the general idea. And specifically, what makes this different from other types of maze games is the fact that you have two additional constraints. Basically, one of them being that you also have an inherent orientation to your agent in this world, and you can see that being symbolized by the fact that this thing here is an arrow, right? So you are facing some direction, and it turns out that the direction you are facing limits the actions you can take, in that you can only go in the direction you are facing. And so if you want to go, say left or right or something, you would first have to turn to align yourself to that direction and then move forward. So what is your kind of overall set of actions? You have the ability to turn left or right, and then you have the ability to go forward. Now, in what way can you go forward? The second constraint is the fact that you have two ways of moving forward, the fast mode and the slow mode. And basically, each time you use the fast mode action, what this does is it increases your velocity by 1, and whatever your current velocity is, you move forward by that many steps. And slow, similarly, what slow does is it decreases your velocity by 1. So basically, whatever you have adjusted your velocity to, you will move forward by that many spaces. And also, what's important is you're only allowed to turn when your velocity is 0. So if you're moving with a non-zero velocity, you cannot turn. Also, in order for you to be done, in order for you to have finished the game successfully, you need to not only be at the goal state, but you also need to be at rest. So, these are kind of the constraints you have for this problem, right? Let's jump right in with problem 1, subpart 1. If the grid is m by n, what is the size of the state space? Justify your answer. So, this is basically like a standard, what is the size of the state space question? And there's a more or less standard way of approaching these kinds of questions, which is you think about what are the variables which I need to store in my state, right? So kind of your first question is, what are all the variables I need in my state? And what does this mean? It basically means, what is the set of all things I need to keep track of in order to know, at what stage I am at in the game, right? So in this case, for example, just like most maze problems, you will need to keep track of what your position is in the maze. Why? Because your position in the maze is what determines whether you are able to move in various directions, right? For example, if you're, suppose that your agent is over here or something and facing in that direction, then your actions are kind of limited because you cannot move forward, right? Or perhaps a different way of saying that is, if you move forward, it's just a self-transition. It takes you back to the same state, right? So where you are determines how you can move, and so it's relevant to your state, which means probably we'll have to store some x coordinate, y coordinate. But in addition, in this game, we also have to store your current velocity, right? Because you have to know how fast you're moving. Why? Because depending on your velocity, that's what determines how many steps forward you go, right? You have a velocity of 4. Then when you take a fast action, say, it's going to go up to 5 and you move forward 5 steps. So you want to keep track of your velocity. Also, there's one more thing which you have to keep track of, which is your orientation, right? Because depending on what way you're oriented, the actions the actions you can take will change, right? So how do we kind of write that in the form of like an actual state space size? Well, basically measure what is the range of each of the variables that you have to maintain, right? So for us, we said there's an x coordinate, y coordinate. What is the range of each of those? Well, it's m and n respectively, right? The problem gives us that. So what we do is we multiply both of those sizes, m times n, right? Okay, what else do we have to store? We have to store also the velocity, right? How many velocity values are there? Well, assuming that the largest velocity you can possibly obtain is v max, which the problem says over here. So if the largest velocity is v max, then you can take all velocity values from 1 to v max as well as 0, because you can also be at rest, right? So it's going to be a total of v max plus 1 values. That's the size of the range of values for velocity. And also you have orientation, and there's 4 possible orientations, north, south, east, west. So that gives you a 4 over here. And just multiply the sizes of each of these ranges, and that will give you the size of your state space. Okay, part 2. Is the Manhattan distance from the agent's location to the exit admissible? Why or why not? So this is kind of your standard question about the admissibility of a certain heuristic. In this case, the heuristic being the Manhattan distance to the goal. Just to recall, what does Manhattan distance mean? Basically, it's the number of hops you would need to take on the grid to get from your current position to the goal, assuming that there was no walls in the way, right? So it's kind of like just the difference between your x values plus the difference between your y values, or I and j values, if you want to use that. So that's what Manhattan distance is. Now, the question is it an admissible heuristic? Recall that the reason why we care about admissibility is because if a heuristic is not admissible, then in lecture we've seen examples of how that might lead to, in A-star tree search, it might end up finding a solution which is actually not optimal, right? So we want our heuristics to be admissible. What does it mean to be admissible? It means that the heuristic is always an underestimate of the true distance from a certain state to the goal state, right? So for this question, basically we're asking ourselves, is it the case that Manhattan distance is always an underestimate of the true distance between any state and the goal? And kind of, for most maze questions which you've probably seen before this, the answer would be that yes, it is admissible, because in most cases, the only thing that's going to happen is, maybe these walls will increase the amount of time you need to take to get from a certain state to the goal, right? And so by kind of relaxing your problem, by ignoring the walls and looking at just Manhattan distance, you are really only underestimating the true distance to the goal, right? So you might expect the same thing to apply here. It turns out it does not. Why? Because of these extra constraints in the problem, right? Because of the fact that your agent might actually move faster than 1 square per action, right? So it might turn out that the agent moves multiple squares per action. Why? Because you also have a velocity factor here, right? So one example of how this might work is, suppose that the grid which you have is just like a single straight line. So it's just one really long hallway, and suppose that your agent is over here, and let's say 6 spots away you have your goal state. So that's 1, 2, 3, 4, 5, 6. So your agent is currently here, and your goal state is over here. Let's forget about that. And suppose that your agent currently has a velocity of 4, right? Now in this case, what is the Manhattan distance between the agent and the goal? It's 1, 2, 3, 4, 5, 6 spaces, right? So Manhattan distance is 6. But what is the actual number of steps that it needs to take to get to the goal? Well, suppose you did the following. Suppose the actions you took were slow, followed by slow, followed by slow. So slow 3 times. What's going to happen? The first slow will decrease your velocity to 3, and you go forward by 3 spaces, right? So you end up over here. The next one is going to slow it down to 2. So by this time it's down to 3. Next one slows it down to 2. You go forward 2 spaces. And then the final one slows it down to 1. You take the final step and you end up at the goal, right? And why do you have to slow down? Why can't you just stay at 4? Because there's the constraint that you have to be at velocity 0 at the goal state in order to be done with the game, right? So here you have an example of, we only took 3 steps to get to the goal, or 3 actions to get to the goal, right? But the Manhattan distance is 6, and 6 is an overestimate of 3, right? So because of examples like this, it's not always the case that Manhattan distance is going to be an underestimate of the true distance from your agent to the goal, and so it's not admissible. The answer is not admissible. And the answer is basically because of what we've described. And if you just gave this thing up here as a counterexample, that would be perfect. So you would get all the points for this question. Okay, so question 3 is about, so in question 2, we found that Manhattan distance is not an admissible heuristic. So question 3 is about, okay, let's try to state some heuristics which are admissible for this problem, right? And the idea is, maybe we can kind of tweak Manhattan distance, right? And we can take into account the fact that that you have this velocity term, and we can come up with a modified heuristic which is in fact admissible. And it turns out we can do that, and we can do that kind of by recalling that we do have a max velocity, right? Which means that whatever velocity you're going at, right, like regardless of what the current velocity is, there's a limit on how fast you can go, and so there's a limit on how quickly you can get to the goal state, right? So what we can do is, kind of as a first attempt at an admissible heuristic, we can say, let's take the Manhattan distance, right, between the agent and the goal state, and let's divide that by the maximum velocity, right? So this thing is going to be a lower bound on what is the amount of time that your agent can take to reach the goal. Why? Because even if your agent is traveling as fast as possible at Vmax throughout the entire duration of the game, right, this is how many steps they're going to take to get to the goal, right? And in fact, actually we can do better than this estimate, because it turns out that it's not really possible to maintain a velocity of Vmax the entire time, right? Why? Because we have to slow down as we reach the goal, right? Because the description here states that you have to be at velocity 0 at the goal in order to actually complete the game, right? So really it's not even possible to be going at Vmax the entire time, but we're just relaxing that constraint. We're saying, even if we could go at Vmax the whole time, this would be how much time you would take, like that's the least possible time you can take, which means this thing is always going to be an underestimate of the true time that you will take, and so it is an admissible heuristic, right? That's one option. One other option is, perhaps we could instead of looking at the velocity, we could look at we could look at the orientation, right? So we know that orientation also matters with respect to which actions you can take. And for example, if your goal is here, suppose that your agent is over here and it's oriented away from the goal like this, right? Now, in order to get to the goal, of course you have to travel all this distance, but in addition to that, what you have to do is you also have to turn to face the goal, right? Because if you're facing this way, there's no way you can move in the direction of the goal, right? So in fact, one possible heuristic value for this state is simply the number 2. Why? Because you need to at least turn and turn completely 180 degrees around in order to be able to go in the upwards direction or north, right? And without going north, you can never reach the goal because the goal is north of you, right? So one possible heuristic is just the number of turns you have to make to face the direction of the goal, right? And so that's our second heuristic, which is number of turns required, right? And it might seem like this thing is maybe kind of trivial, right? Like you might think, this number is never going to be more than 2, right? Because at most you have to turn 180 degrees, right? And that's true. This is definitely not as good an estimate of the distance to the goal as this is, but it's still an admissible heuristic, which is not just like the 0 heuristic, and so it does count as a valid answer to the problem, right? In fact, one thing which you could do is you could actually, in this case, for this particular problem, you could even add both of these, and the result would also be admissible, right? Why? Because in this case, suppose that you are at this state, not only do you have to turn to face the goal, you also have to travel the distance, right? So kind of those two quantities down there are disjoint, and you have to do both of them to reach the goal. So by adding them, it still remains an underestimate of the true distance. Note that this is not true in general. In general, adding two admissible heuristics is not necessarily going to maintain admissibility. But in this case, because of the structure of the problem, it happens to be true, right? One more option we can add in is to say, basically take the first answer and correct for the fact that actually you cannot be traveling at Vmax the entire time. Right, so what this will do is, probably you'll change the denominator to be something which is a little bit smaller than Vmax, maybe some kind of adjustment term for the fact that you have to slow down once you reach the goal. And so this overall quantity will be a bit bigger, making it a better heuristic, but it'll still be an underestimate of the true distance to the goal. So basically we would say that the resulting heuristic dominates this heuristic in the sense that for every state it's going to be a better estimate, but it's still going to be admissible, right? So our third option is take into account slowing down, right? We're not going to go into the like the actual equation which you need to find to take into account how much you slow down, but it shouldn't be too difficult to do. And a good exercise is to try to derive what that's going to be. Okay, so part 4. Part 4 is also about admissibility of heuristics. So it's asking if we used an inadmissible heuristic in A* graph search. Let's underline graph search so we know we're dealing with this as opposed to tree search, right? Would the search be complete and would it be optimal? Okay, so recall that completeness refers to an algorithm which if there is a solution, it is able to find the solution, right? And optimality refers to it always finds the best possible solution, that is the lowest cost solution, right? So first, to answer the question, would search be complete? Well, we kind of have to think about what are the properties of A* graph search. Well, we know that A* graph search does not revisit any vertices that it's already visited. And what this means is that as long as there is a path from your start state to the end state, right? So as long as a solution exists, A* graph search is going to terminate and it will find that solution. Why? Because since you never revisit an already visited node, A* graph search will continuously be exploring new nodes until it finds the goal state, at which point the algorithm is done, right? So the answer for completeness is that yes, it is complete. And the inadmissibility of the heuristic does not affect this because this is just a property of how A* graph search expands nodes, right? Okay, what about optimality? Well, we know that both in the case of A* tree search as well as A* graph search, if you have an inadmissible heuristic, it's not necessarily going to give you the optimal solution. And we've seen kind of examples of this. One example is suppose you have a simple graph with just 4 states. You have a source, a goal, or start, a goal, and you have an A and a B state. Let's assign some edge weights. Let's say these are both 1, and then here this one is 1, this one is 2. Let's also assign heuristic values. So the heuristic values I'll write next to the nodes. Let's say it's 0 for this, 0 for this, 0 for this, and 4 for this, right? Now what will A* graph search as well as tree search do in this situation? They'll start at S, and now what you would want the algorithm to do is to take the path on top because it has a true cost of 2, whereas the path on the bottom has a cost of 3, right? Now what would A* do? It would notice that this node looks like it's very high cost because of this 4. This 4 causes the cost to be 5. Whereas here the cost of B looks like it's just 1, so it's going to take B. Now once it takes B, the cost of going from B to G is also going to seem lower than the cost of visiting A, because now that's going to be 2. It's 2 plus 1, which is 3, whereas the cost of visiting A is still 5, which is too big. So it then visits G, at which point the algorithm is done, and it returns SBG as the path when really you would want to return SAG, right? So simple counterexample for how an inadmissible heuristic causes A* to be suboptimal, right? And what makes this inadmissible? It's the fact that this 4 over here is an overestimate of the true distance to the goal, right? The true distance from A to G is 1, and 4 is bigger than 1. So the answer for this is not optimal. Okay, part 5. Part 5 is if we used an admissible heuristic in A* graph search, once again A* graph search, is it guaranteed to return an optimal solution? What if it was consistent? Okay, admissibility versus consistency. So the idea is, in the previous one, in part 4, we saw that if you have an inadmissible heuristic, then it does not necessarily give you an optimal solution for A* graph search. So you might expect, okay, if it's admissible, then it probably does give us something optimal. And in fact, that is true for A* tree search. But one of the differences between A* tree search and graph search is exactly this: the fact that an admissible heuristic does not guarantee optimality for graph search. Now, why is that? Well, we can take kind of a sample graph which is very similar to the one above. In fact, let's just use this and let's modify it a bit. I'll call this C instead of G, and the goal state I will add over here. Let's make this edge weight be 3. So this is now the goal state, and let's have everything else be the same, right? So now, are these heuristic values admissible? In fact, they are. The only issue before was the 4, but 4 is now no longer an overestimate because 4 is equal to 1 plus 3, right? So now it's still admissible. Now in this case, what's A star graph search going to do? It does the exact same thing as before, right? So it starts at S, this A looks very high cost, so it goes to B, and then it goes to C. And then the thing is, once it visits C, because we're talking about A star graph search, this node gets added to what you would call the closed set. That is the set of vertices which have been visited, and so you are not going to visit it again over the course of the algorithm, right? Which means that the algorithm will never find the path SAC, and so it will never give you SACG, which is the true optimal path. Instead, it will give you SBCG, right? So this is kind of like the classic example for why an admissible heuristic does not give you an optimal solution always in the case of A star graph search. So is it guaranteed? The answer for this is no. What if the heuristic was consistent? Well, yeah, so basically forcing the heuristic to be consistent is what will ensure us optimality in the case of A star graph search. So the answer for this is yes. And as a refresher, what is consistency? It basically means that in addition to being admissible, that is, in addition to underestimating all the true costs from each node to the goal, you must also underestimate the cost of each edge. And what that means is, for example, if I look at this edge over here, right? What does it mean to underestimate the cost of the edge? It means if I take this heuristic value minus that heuristic value, which is 4 minus 0, that is supposed to be less than what is the true cost of this edge if I want consistency. But in this case, this minus this is 4, whereas this is 1, and this is clearly not true, right? If this was true for all the edges in the graph, then the heuristic would be consistent, and in fact, it would give you an optimal solution even for A star graph search. And there's a proof of this which you can take a look at in the notes. I would certainly encourage that you take a look at that. Number 6 is give an advantage that an inadmissible heuristic might have over an admissible one. So, even though inadmissible heuristics don't always give us optimal solutions for A star search, that does not mean that they're completely useless. So in particular, the main advantage which this question is asking about is the fact that inadmissible heuristics might be easier to compute compared to admissible ones. Because for inadmissible heuristics, you don't have to care so much about whether it's an overestimate or underestimate. You can just try to find some value which is close to the true distance from each state to the goal. And if it overestimates, that's fine. Maybe you don't have to put as much computation into finding the solution, and so it might be easier to find the solution, right? So less computation is the main one. And less computation means that your algorithm might have a smaller runtime. And so maybe if you're dealing with the kind of problem where you care less about optimality and more about how fast you want to get some solution which is reasonably good, you might use a heuristic which is inadmissible. So problem 2 is called course scheduling. It's our first CSP problem in discussion. And it's basically more or less just a mechanical CSP problem. So, just walking you through an example of how to set up a CSP. And the problem is formulated as you have a bunch of classes. You have 5 classes, and each class meets at a certain time. And you have professors who have to teach each of these classes. Now, each professor has certain qualifications. There's some classes which they can teach. And the constraint which you have to satisfy is that you can't have one professor teaching 2 classes which both overlap in their timing, right? That's the constraint you want to satisfy. And part 1 is to formulate this as a CSP problem. Feel free to pause and take a few minutes to read through the description, but I'll be getting started with part 1. So part 1 says formulate it as a CSP where you have one variable per class, stating the domains after enforcing unary constraints as well as binary constraints. Okay, so what this means is we're going to have one variable for each of these classes, so 5 variables. Let's write those down. C1, C2, C3, C4, and C5. These are our variables. Let's write the domains of each of these variables. So what's it going to be for C1? What is the set of professors who can teach the first class? Well, the first class appears here as well as here, which means Professor A and C can both teach the class. So the domain of this is going to be A and C. Similarly, C2, who's qualified to teach class 2? Well, it only appears here, which means that only Professor A is qualified to teach this. And similarly, we can fill out the rest of this. C3, 3 appears here and here, so it's going to be Professor B and C. C4 appears here and here, also going to be B and C. C5 appears here and here, so it's going to be A and B. Okay, and what about the binary constraints? Let's write those over here. Binary constraints. So the constraints we have are that you cannot have a professor teaching 2 classes that overlap. So which are the classes that overlap? Well, we have that class 1 and class 2 overlap. This is 8 to 9, this is 8:30 to 9:30. There's a half an hour overlap, which means that whichever professor is assigned to class 1, right, that's going to be the value of the variable C1. It cannot be the same as the professor who is assigned to class 2. So C1 is not equal to C2, right? That's a binary constraint because it involves just 2 of the variables. And let's keep on going for the rest of the classes. So class 2 and class 3 also have an overlap, which means let's add over here C2 not equal to C3. And which ones are the other ones? Well, it seems that class 2 and class 4 have an overlap. Class 3 and class 4 fully overlap, in fact. And class 5, it seems, does not overlap with any of the others. So there's these two. There's C2 not equal to C4 and C3 not equal to C4. And that's all the binary constraints. Note that the reason why we didn't write any unary constraints is because we kind of absorbed them into these domains, right? We could have equivalently written these domains as just, A, B, C for all of these, and we could have added unary constraints saying things like, for example, C1 cannot be equal to B, right? Because Professor B is not qualified to teach class 1. But usually for unary constraints, we absorb them into the domains by just pruning the domains and removing everything which is disallowed by the unary constraints. And that's what we also have done here. So that's it for part 1. Part 2 is draw the constraint graph associated with your CSP. So the constraint graph for a CSP, typically the way we draw it is we have the nodes represent the various variables that we have in the CSP, and the edges represent the binary constraints that we have. And this is assuming that the only constraints we have are binary constraints. If you have constraints on 3 or more variables, then it's going to be difficult to represent that with a graph. So usually this kind of representation is used only when you have just unary and binary constraints, right? So let's draw that. We have our binary constraints over here. So you have an edge between C1 and C2. Let's draw these: C1, C2, C3, C4. So C1 and C2 share an edge, C2 and C3 share an edge, C2 and C4, as well as C3 and C4. And C5 does not share an edge with any of these because there's no constraints involving C5, so that will just be an isolated node over here. Note that we're using undirected edges because there's no inherent directionality in these constraints that we have over here. It's just some constraint involving these 2 variables or these 2 variables and so on and so forth. So we have these edges be undirected. However, when we do arc consistency, we'll be replacing these undirected edges with directed edges in each direction, and we'll see more about how that works in the next problem. But that's it for problem 2 of the worksheet. Okay, let's get started with problem 3. So feel free to take a minute to just pause the video and read through the entire problem, but I'll just be getting started with the first part. So basically the setup in this problem is you have this Pac-Man, and Pac-Man is trying to decide which of these doors to go through, and there can be one of three things behind these doors. You could have a pit, you could have an exit, or you could have a ghost. And Pac-Man, of course, wants to go to the exit and wants to avoid the other two, right? And the idea is that you can get information about what is behind these doors based on what kind of breeze is blowing at the intersection of these doors. In particular, a pit produces a strong breeze, an exit produces a weak breeze, and a ghost does not produce any breeze at all. And you get to measure the breeze at the intersections between these doors, and the breeze which you see is the max of the breezes which are blowing in the adjacent doors. So for example, if you have two pits side by side, then you'll be getting a strong breeze between them. If you have one pit on one pit on one side and you have an exit on the other, it'll still be strong. If you have an exit and a ghost, it'll be weak. And one of the constraints in the problem is that you will not have two exits side by side. Okay, so part one is to state the binary and or unary constraints in the CSP, either implicitly or explicitly. Okay, so let's use xi to represent each of the variables, which means that we're going to have basically 6 variables, so x1 through x6. Let's start by let's look at this piece of information we get in this picture, that is at the intersection of x1 and x2, that is door 1 and door 2, we see a strong breeze. Now what does this mean? It means that the max of both of these breezes is strong, which means that at least one of these has to be a pit, right? Because if neither of these was a pit, then you would not be getting a strong breeze over here, right? So that leads us to our first binary constraint, which is either x1 is a pit or x2 is a pit. Okay, let's also look at maybe what the constraint is going to give us over here. So here you have a weak breeze between door 2 and door 3, which means that at least one of these has to be an exit, because exits are what produce weak breeze, right? So that gives us one more constraint. We have that x2 is equal to an exit, or x3 is equal to an exit. And we can apply the same logic to all of the intersections. So just like we saw a strong breeze over here, we can get one equation just like this for all the other strong breezes, and we can get one more equation for the weak breeze over here. So I'll just quickly fill all of that out. Okay, so here we have all the equations corresponding to each of these intersections. Now, in addition, we also have some other constraints which are specified by the fact that we cannot have two exits side by side, right? So how can we write that? Well, that's going to be basically, not just one binary constraint, but it's going to be a bunch of binary constraints, and we can write that using a concise notation. We can say maybe for all I and j, such that you have I and j being adjacent, for which we can maybe use this notation as shorthand. What do you have being true for these? You have that you cannot have, it is not true that you can have xi being equal to exit and xj being equal to exit, which, overall this means that you cannot have any two exits side by side, right? So these are all the binary constraints. You also have some unary constraints, and these you can deduce from the fact that over here, because these are both weak breeze, it also gives us some extra information about what is behind doors 2, 3, and 4. In particular, it tells us that you cannot have a pit behind any of these. Why? Because if you did, then the pit would result in a strong breeze blowing at this intersection in the case of 2 or 3, or this intersection in the case of 3 or 4, right? So none of these three can have pits behind them, and so the unary constraints are x2 cannot be a pit, x3 cannot be a pit, and x4 cannot be a pit. So these are the unary constraints, and here we have binary constraints. And those are all the constraints described in the problem. So that's it for part 1. Okay, so now let's start with part 2, which is about arc consistency. So basically, arc consistency is a technique which allows us to greatly simplify the process of backtracking search, which will eventually lead us to some kind of solution for the CSP. And the idea of arc consistency is the following. It's you take a constraint graph similar to the one which we drew for the previous problem. And what will that constraint graph look like for this problem? Well, it's going to look kind of like, you have nodes for each of these variables. So you've got 1, 2, 3, 4, 5, 6. And what are the edges? The edges correspond to all the pairs of variables for which you have binary constraints. And in this case, that's just each adjacent pair, which means it looks something like this. Right? That's what your constraint graph looks like. And the idea of arc consistency is you want to take each edge of your constraint graph and you want to kind of think of it as an arc this way and an arc this way. In this case, arc just means something like a directed edge, right? And you do this for all of your undirected edges in the graph. So, do that for all of these and so on and so forth, right? And take all of these. So there's 2 per edge in this case, and there's 6 edges. So there's 12 of these arcs, and you add them all to a queue, right? And one by one, you look at these arcs, and for each arc, you do the following, right? So suppose that the arc which you're currently considering is one which goes from x1 to x2, right? Here's what you want to do. You want to ask yourself the question, is it the case that for every remaining value in the domain of the variable at the tail, which in this case is x1, for each value in the domain of this, is there some value in the domain of this such that if you assigned both of those values to each of these variables, it would satisfy all the constraints of the problem? So, basically I'll repeat that one more time. Is it the case that for every value in the domain of this, you have some value in the domain of this, such that if you assign those values, they obey all the constraints, right? Now, if the answer is yes, then you're good, and you can move on to the next value in the domain of the variable at the tail. But if it's not true, then you would delete that value from the domain of the variable at the tail, right? Now, this is best made concrete by doing an example. So let's actually perform this on all of these domains for these variables over here, and let's see what we get. Actually, before starting our consistency here, what I will do is I will enforce all the unary constraints, because one way, as we discussed earlier, of enforcing unary constraints is to just prune the domains of each of the variables, right? In this case, we know x2, x3, x4 cannot be p, so let's just cross those out. x2, x3, x4 cannot be p. Okay, so we've simplified our job a bit. Now let's look at the arc from x1 to x2. Okay. Now let's just go one by one for each variable in the domain of x1. So if I assigned p to x1, is it the case that there is something, some value in x2's domain which satisfies all the constraints, right? And in this case, the answer is yes. We can go up to our constraints over here, and we notice that yes, in fact, if we assign p to x1, that satisfies this constraint over here, right? Which is the constraint that at least one of x1 or x2 must be p, right? Why? Why was that? Going back up here, that's because we had a strong wind over here, right? So assigning p to x1 already makes this be true, and none of the other constraints are relevant to the arc between x1 and x2, which means that all the constraints in fact get satisfied, right? I guess perhaps this constraint is also relevant, right? The constraint that you cannot have 2 adjacent exits, but this is satisfied because it's not the case that these are both exits, right? So regardless of whether I assign G or E to x2, there is some satisfying assignment from the variables which are in x2's domain, right? Which means P is safe. Okay, what about G, right? If I assign G to x1, is it the case that I can assign some of these two variables to x2 such that all the constraints are satisfied? Now in this case, the answer is no, right? Why? Because if I assign G to x1, then, well, I cannot assign P to x2, which means that this constraint will end up being violated, right? I will end up having neither x1 nor x2 being a pit, right? Which means that it is not possible to satisfy both of these. It's not possible to satisfy all the constraints if I assign G to x1, which means I have to prune G from the domain of x1, which I do by just cancelling it out. And then same process for E. If I assign E to x1, is there some value over here which I can assign to x2 which satisfies the constraints? Once again, the answer is no, because if I'm assigning E to x1, I cannot assign P to x2 because it's already crossed out, and therefore this constraint cannot be satisfied, right? So E also is off limits, right? Note that when I'm considering the arc from x1 to x2, I'm only deleting things from the domain of x1, right? That's like an important note. You're only deleting things from the domain of the variable which is at the tail, not the one that's at the head, right? And in this case, we are done with this arc, so we can remove this from our queue. We can move on to the next arc, right? Perhaps the next arc, let's walk through one more arc. So let's say it's the arc from x2 to x1. In this case, let's see if everything's satisfied. And note that in general, the reason why we consider both of these directions separately is because it's not the case that if one is satisfied, the other will be satisfied. Okay, now let's see if this arc is consistent. Now if I assign, P is already off limits, so if I assign G to x2, is there something which I can assign to x1? Yes, if I assign P to x1, then this constraint is satisfied, right? And all the others are also satisfied. So G works. I'm not gonna prune G, right? If I assign E to x2, the same thing is true, right? P is available, I can assign P to x1, and so this thing is satisfied, and so is everything else. So it turns out that for this arc, I actually don't have to remove anything, right? And we can continue the same process for all the arcs, right? I'm not going to walk through the whole thing because we have 12 arcs, and it'll take a long time to get through all of them, right? But the idea is, let's just kind of roughly see what's going to happen. Does everything work for x2 and x3? Well, yes, it is going to work, because if I assign G to x2, right, like what is the constraint between x2 and x3? We have that at least one of them must be E, right? So what I can do is, if I'm assigning G to x2, I can assign E to x3, and so this one is consistent, right? And if I assign E to x2, I can then assign G to x3, and once again that confirms that both of these values are consistent for the arc going from x2 to x3. And the same logic applies for this arc. The same logic applies for the x3, x4 arcs. So both of these, right? So nothing ends up getting removed from the domains of x2, x3, and x4. The next kind of interesting thing comes when we are looking at the arc from x5 to x4. So this arc over there, right? Now what happens is, first let's consider P. So if I assign P to x5, maybe let's scroll up again to remind ourselves what x4 and x5 look like. So that's x4 and that's x5, right? If I assign P to x5, so if this thing is P, then that satisfies the constraint that we have for x4 and x5, which is this one, right? At least one of them must be P, right? Which means I can assign whatever I want to the other one. I can assign whatever I want to x4, either G or E, and everything is going to be satisfied. So P is good. However, it does not work for G and E, right? If I assign G to x5, because I cannot assign P to x4, there's no value I can assign which satisfies this constraint, because neither will be P. So I will have to remove G. Basically, the same thing which happened with x1 and x2 is now happening with these two, right? And for similar reasons, we also have to remove this. And also, one interesting case is what happens with x6 and all the rest. It turns out that we don't have to remove anything from the domain of x6, because what are the neighbors of x6? There's x5 and there's x1. And in each of these cases, there is always something which I can assign in either x1 or x5, which satisfies each of these for x6, right? Because what is the only constraint involving, x1 or x5 and x6? It's these constraints, right? There's this one for x1 and x6. There's this one for x5 and x6. And they just say that at least one of the pair, x1, x6 or x6, x5 has to be p, right? And that'll always be the case because the values which I'm assigning to x1 and x5 can only be p, right? So regardless of whether x6 is p or g or e, because these values are here, I can always satisfy these constraints. And so actually nothing gets pruned from 6. And this is what you end up getting when you enforce arc consistency for all of these variables. We didn't go through the the formal kind of algorithmic process of popping one of the arcs off of the queue and doing the analysis for all the arcs, and then sometimes adding back to the queue if you make changes to some of these variables. But that's just because we have too many arcs in this problem. I would encourage you to actually walk through it, even though it is kind of pretty long to walk through all the arcs. Just do that once and make sure that it matches up with what you see over here, just to kind of confirm that this stuff actually works. But that's the answer for part 2. Okay, now let's move on to part 3. So according to MRV, so recall that MRV refers to the minimally restrained variable heuristic. So part 3 asks us, according to MRV, and recall that MRV refers to the minimum remaining values heuristic, right? So basically, it's a way that we can decide which of the variables we want to choose next to assign some value in backtracking search, right? So the question is, according to MRV, which variable or variables could the solver assign first? Okay, so let's write this down. Minimum remaining values. And the idea of this is basically, when backtracking search is to decide which variable it is going to assign a value to next, it looks at all the variables and it chooses one of the ones which has the least number of values left in its domain. Now, why would you want to do this? The idea is basically that, if you assign some value to whatever has the least values remaining, then if in the future you have to end up backtracking, right? If you backtracked back to this point, then you've already failed, right? Because there's like no other values you can possibly assign to this, right? The idea is if looking at these variables, for example, if you assign, say, x6 some value to begin with, right? You may have to backtrack all the way back to this step and then realize that, oh, I shouldn't have assigned this p over here. I should instead have assigned g, right? So it's kind of like when you backtrack, you're backtracking a long way up the search tree. And we want to avoid that by assigning variables like x1 and x5 first, right? Because if say you assign p to x1, now if that goes wrong somewhere down the line, it's not like you're backtracking all the way back to this choice and saying, oh, I should have chosen something else, right? So it's kind of like, if anything is going to work, it's going to be this one. So let's go ahead and assign this to this variable. So that's kind of like the intuitive idea. So what's the answer to the question? Well, we would assign either x1 or x5 because they both have just one value left in their domain. And that's the least among all of these variables. So the answer is x1 or x5. Okay, so part 4. Assume that Pac-Man knows that x6 is a ghost. List all solutions of the CSP or write none if no solutions exist. Let's scroll up here and just work up here while we're solving this. So we know that x6 is a ghost. Now what is this? So what does this tell us? We know that ghosts do not produce any breeze, right? And so what that means is if you have a strong breeze over here and over here, it cannot be due to this ghost. And so it must be due to the fact that you have a pit over here and a pit over here. there's no other way that you could get strong breeze in both of these junctions, right? So we immediately know that both of these have to be P, right? So now all that's left is to decide, what's at 2, 3, and 4, right? Now kind of, the only constraint you have now on 2, 3, and 4 is provided by these weak breezes over here, right? Because these strong constraints are already taken care of by the P here and the P here. So we only have to think about what these W's tell us, right? And like this thing being W means that one of these has to be an exit, and this being W means one of these has to be an exit. So one thing which you can do is you can say, maybe this thing is an exit, that is 2 is an exit, and 4 is an exit, and this one could be a ghost over here, right? Or it's possible that this one could instead be an exit, and this in fact takes care of both of these W's, right? This exit can produce both of these weak breezes, and here you can have what's remaining, which is you can have a ghost over here and a ghost over here. Note that the reason why we're not considering a pit for any of these is because of the constraints that we have down here, these unitary constraints, right? None of these 3 can be pits because of these weak breezes, right? And you might be asking, why didn't we also assign an exit over here, right? Like, why is it not possible to have exit, 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 exit? That's because the problem states that we cannot have 2 exits which are adjacent, right? So, finally we're using this constraint down here, right? If we had all 3 of these being exits, 2, 3, and 4 all being exits, that would violate that constraint, right? So here we have the answer. The answer is the solutions are P, E, G, E, P, G. This is for x1 through x6 respectively, or it could be P, G, E, G, P, G. The difference is just in these 3 over here. And so these are the 2 solutions. Okay, now let's move on to question 5 and question 6. Okay, now let's move on to part 5 and part 6. So these deal with kind of a modified version of the above scenario, where instead of having 6 nodes which are all connected in this circular manner, now you have n nodes in general which are connected in this kind of circular pattern, right? And all of the constraints are binary constraints, and they are constraints on adjacent variables, similar to how it's shown over here. Now the question, part 5, is asking, explain how to solve this efficiently using methods covered in this class. So it turns out we can use arc consistency to reduce this to a problem that we know how to solve very easily using existing methods, right? I'll just jump straight into the solution, which is, the way you can do this is choose any one of these variables. I'll arbitrarily choose one, and let's assign it some value in its domain, right? Effectively, what this does is it removes this variable from consideration when we're assigning all the rest, right? Now, because we're kind of ignoring this for the remainder of the algorithm, it might be the case that there's some conflicts later, but we'll resolve that when we get there, right? For now, this thing has been assigned some value, and we're not considering anymore. Okay, so what can we do next? Well, notice that basically with this thing gone, the remaining graph has the structure of just like a linear chain, right? It's just from 2 to n, it's just a straight chain where each node is linked only to the next one, right? Now what this means is, like maybe you could call it a line structured CSP. In particular, this also means that it's a tree structured CSP, right? So this CSP which you have now is tree structured. And we know a very efficient way of solving tree structured CSPs, which is by using arc consistency, right? So suppose we just ran our consistency on the rest of this graph. So, like everything from 2 through n, right? After we finished running our consistency, what do we get? Well, suppose that we wanted to assign some value in 2's domain to the variable x2, right? Okay, suppose we did that. And then after that, suppose we wanted to assign some value in the domain of x3 to x3. Okay, so after we run our consistency, let's just choose to assign x2 some value in its domain, right? And suppose we've done that. Okay, now we get to the point when we want to add some value in x3's domain and assign it to x3. Okay, so assume we've run our consistency, and suppose that now we look at x2 and we assign it some value in its domain. Now we want to assign x3 some value in its domain, but normally what we would have to consider is we want to make sure that there's no constraint violated when we do that, right? But the great thing is our consistency ensures for us that for every value that remains in the domain of 2, there is some value in the domain of 3, which you can assign to x3 and keep all the constraints satisfied. Which means really after you've run our consistency, you can just assign some value to this, assign something to this, something to this, and so on and so forth. And you are ensured that at each step of the way, the assignment that you are making is consistent with all the constraints, right? Because for each value in this, you have something here. For each thing here, you have something here, and so on and so forth, all the way until n, right? So you can just make one pass and assign values to all of these variables. And at this point, we're almost done. The issue is that the assignments that you've made to 2 and n might conflict with the assignment you made to 1, right? So it's possible that among these 3 over here, there's some constraints violated, right? Now, how do we resolve this? Well, if that's the case, then we can simply redo this whole process with a different value chosen for 1, right? So, like instead of assigning 1 whatever value it had before, assign it one of the new values in 1's domain, rerun our consistency, and then repeat the whole process, and keep doing this until either you've exhausted all the values in 1's domain, or you found some assignment of values to the variables which is consistent with all the constraints, right? And that's how you solve the problem, right? So you can convert to a tree-structured CSP by conditioning on one of the variables. And once you've done this conditioning, you can solve things efficiently using just our consistency, right? Which means basically your algorithm is going to be as efficient as d runs of our consistency, where d is the size of the domain of whichever variable you are conditioning on. And that's the answer to part 5. Now part 6 is asking us, if standard backtracking search was run on a circle-structured graph such as the one above, and we enforce our consistency at every step, what can be said about the worst-case backtracking behavior? And for this, like this kind of comes out of our answer to the previous part, that is part 5. So the way backtracking search would work is it would start with some variable, right? So let's say arbitrarily it starts with 1, right? It would choose some value for 1, and then it would run our consistency on the rest of the graph, right? Now the thing is, this is effectively doing the same thing that we were doing in part 5, right? So it's assigned some value, it's assigned some value to 1, and then it ran our consistency, right? Which means that it's possible that the resulting assignment to the rest of the variables. Now we know that once some value has been assigned to any one of these variables in the circle by the backtracking search algorithm, right? All of the remaining assignments are going to be, just one single pass. Why? Because you've run our consistency, and every assignment you make after that is going to satisfy all the constraints until you reach n, right? The only issue is if at some point one of these variables does not have anything left in its domain after you ran our consistency, in that case you will have to backtrack, right? And what happens when you backtrack? will, backtracking search will go back to this very first variable it assigned a value to, and it'll change that value. And then it'll do the whole process again, right? So the question of, what's the number of times that you backtrack in the worst case? Well, that's basically the same as the answer to this, right? So in this thing, you run R consistency at most D times, because each time you're exploring one value for the variable that you condition on. And similarly, backtracking search will backtrack in the worst case D times, because each time it's assigning some value to the first variable that it happened to choose, right? So the worst case backtracking behavior, worst case it backtracks D times. And that's the answer to part 6.